So, today's class we will discuss about design of a berthing structure. So, first of all we need the information of soil profile. This structure is called as WQ6, is located at Vizag port. They have initially done a soil investigation. So, we have the natural ground occurring like this, you have water this side and the general level of the ground at present is +3. So, from +3 to -4 there is a filled up soil. From -4 to -17 we have a soft marine clay. I discussed about N, the typical value of N in this is about 1, 2, 4 like this, at different depths different values. So, we are assuming the cohesion as 12 kilonewton per meter square. This filled up soil is some kind of sand for which we are assuming phi is equal to 30 degrees. Then we have a residual soil, it is called as residual soil, it is nothing but some kind of sand and mixed with clay, for which we are assuming the phi value as 35 degrees. All these informations are coming from the soil investigation report. Then from -22 to -29 we have the rock which is called as condylite or granite rock. The cohesion for this is about 700 kilonewton per meter square. We will discuss about detail about soil investigation in another class. But what we want to do in this class is, I want to tell what kind of structure we are going to propose at this location, and then analysis using a package called as Staad Pro. This is a finite element software using finite element method. How many of you have used this software, Staad Pro? All civil engineers, all are civil. So, Mr. Afreen will demonstrate tomorrow. I will not be taking class tomorrow, he will be demonstrating that in the next class. First of all, what we have to do is, we have to find out what is the size of the vessel, dead weight tonnage. Dead weight tonnage is about 100,000. This is the size of the vessel which you want to design. One of the important parameter for this is about the draft. Draft is about 13.5 meter in the first phase, to be increased to 16 point minus, not call it as draft. Dredge level will be from -13.5 meter in phase 1 to -16.1 meter in the second phase. Another important criteria is what is the type of structure which you have to do. We are going to do a pile supported structure with diaphragm wall and racker piles. Then what is the crane they are going to use for this? They are going to use two types of crane. One is called as the mobile harbor crane, another is a portal crane. This portal crane rail spacing is 12 meters center to center. So, the crane rail spacing is 12 meters center to center. So, that means you need two rails, one on the sea side, another on the land side. The spacing is about 12 meters. Now, we will see the layout. First we have to fix the top level. Top level is fixed as 3.85. That depends on what is the high water level and all. Natural ground level is +3, but we want to keep this level as 3.85. The dredge level for design purpose we want to take it as -17. So, in the second phase 16.1 meter is the dredge level, but we are increasing because there will be some more dredge allowance and sounding accuracy and all. Then we are keeping one pile here from the face of the berth, that is at a distance of 2.5 meters. It is shown as 2, but we have revised it as 2.5 meters now, because we have to fix a bollard here. There is some services should come here, because of that reason we have revised. Then we have put a diaphragm wall at a distance of 3 meters from the center line of the front row of pile. The the diaphragmal and pile cannot be very close. The minimum distance required is 3 times the diameter of the pile or 3 times the thickness of the wall. We have assumed 1000 millimeter as the thickness of the wall, 1 meter as the diameter of the pile. So we can keep 3 meter, less than 3 meter we cannot keep. If we take, we have to take what is known as group effect, it cannot be very close. The next pile we are keeping at 9 meters. This 9 meter we have fixed because the distance between, here we have one rail, this is called as land side rail, another rail is here, this is called as a seaside rail. So the distance between from here to here is about 12 meters, so that the crane will move on this. The next row of pile is about 6 meters, then we are putting a raker pile that is at a distance of about 6 meters, then we are putting one retaining beam here, there is a beam, crane beam, there is another crane beam, there is a diaphragm wall, on top of it we have another beam, and we have one cross beam which is connecting, this is the cross beam which is connecting all the piles, and we have provision for fenders here. And these piles are at every 4 meters center to center in the longitudinal direction, the other direction, and this diaphragm wall is a continuous wall. One of the reason we want to go for this alternative is there is an active edge. Active edge is here, it is a clay soil, so the active edge will be 45-degree line. So if we take a 45-degree line over this, it will be within the deck, so that any load what is coming here, surcharge load, will not give any active earth pressure. So active edge means the soil will collapse when the diaphragm wall is moving like this. So for that reason we want to keep there is a load on top of the deck, that is 50 kilonewton per meter square, on the backfill also 50 kilonewton per meter square. There is a rail, another rail over which the crane will move. All the loads what is there on the deck will go to the diaphragm wall and piles, it will not go to the soil below. So if the deck is too close, the surcharge load will go transmit some force on the main diaphragm wall, that is why we want to keep it here. The diaphragm wall, instead of keeping it here, we can keep it here also, but as you see here water is there very close by, so we cannot build the diaphragm wall too close, that is why we have shifted the diaphragm wall one pile row behind. So now we will see how to do a Staad Pro analysis for this, for which what we want to do is we want to model springs below this dredge level for the pile, here also below the dredge level for the piles for the diaphragm wall, then we assume a 45-degree line, and then we put the spring below this for this pile as well as for the other pile also. Finite element discretization is a 2D analysis in which we take a typical 4 meter panel, we idealize the pile, beam, pile, vertical pile and diaphragm and raker pile as beam elements, and the deck system also by beam elements. We do not model the slab which is connecting the beam, it is about 350 thick, and we apply the forces, various forces acting on the structure and do the analysis. You show the Staad Pro. Now you will see the model how it is being generated. So this is the Staad Pro model. So this is the place where we are attaching the fender, this is the pile, this is the diaphragm wall, this is another pile, then you have the inclined pile. The springs are starting at different levels depending on the active edge what we are assuming, 45-degree line what we are assuming. And then at the bottom we are assuming a hinge condition, this is to model the rock where it is getting the embedment. So rock can be assumed as a hinge support, that is why we are giving this, and then we will show the various forces considered in the analysis. Show the 3D view. So this figure shows the rendering of the whole things. Rotate, just keep it here, rotate. So if you see here, this pile is 1 meter diameter, this diaphragm wall is 4 meter width, we are taking a typical panel, there is one more pile coming after 4 meters. So we take only a typical panel. So on top of this diaphragm wall we have a beam for 4 meter that we are modeling, at the end we have a retaining beam that is also we are modeling, and there is a cross beam which is connecting all the system together, that is also being modeled. Any doubt in this? I am going little bit fast today. In one class you may not be able to understand everything, you need some more classes. So just whatever you understand you please understand, about 50% if you understand it is okay, the balance 50 you can sit in front of the system and use it. This Staad Pro is a versatile program, it can be used for civil, mechanical and aeronautical and other purposes also. You have understood the view now, here there will be a dredge level, this is 17.5 meter, back side there will be full soil is here, but there is an active wedge here going. So this soil will be sliding, suppose the diaphragm wall is not there, if you fill up the soil what will happen to the soil? Soil will slide down, that is that 45 degree wedge what we are assuming, and the soil itself is sliding, it will not offer support, that is why we are not offering support below this active wedge line, above this active wedge line, only below that we are putting the spring. So now we will see what are the loads we are considering. First we will see the dead load. So we are putting the self weight of each member what we are doing. Second load is earth pressure. So the earth pressure is acting on the diaphragm wall. This calculation I will show in the next class. When the soil is sliding here, if the diaphragm wall is not there, the soil will collapse. Since the diaphragm wall is there, when the soil is sliding, the weight of the soil will exert some pressure on the diaphragm wall, that is called as active earth pressure. Active earth pressure means when the wall moves away from the soil, then it is called as active earth pressure. There is a soil which is sliding, because of the sliding of the soil this diaphragm wall will move, this movement is away from the soil, that is called as active earth pressure. There is procedure to calculate, so that active earth pressure is shown here. Next. Then we have removed the soil below this level, I will tell you why we have removed the soil above this level. We removed above this level because to reduce the earth pressure on the main wall. So that earth pressure will go on the back side. This is the earth pressure due to the soil as well as due to the surcharge load. Then we have the differential water pressure. Differential water pressure means this side of the sea the water level will go up and down, this going up and down will be based on the tidal range. Here we put what is known as a good drainage condition. So whenever the high tide water comes it goes inside, and there is a groundwater due to rain that also comes here, but when this water goes down, this water does not go down with the same phase, that means this will go faster and this will go slower, that means this acts like a water tank and you will have some differential water pressure. The water pressure is about 0.58 meter height, that is given about 58 kilo, I am sorry this is for 4 meter width. So about 1. See here what we have to do is this 58.2 is calculated based on some differential water pressure, but this 58.2 meter is occurring over a panel width of 4 meters, 58.8 kilonewton per meter. So this will be equal to kilonewton per meter square. What it means is this water level is here and this water level is here, this difference between these two water level is about 1.455 meters. I will show the exact calculation for this, and that is acting over the diaphragm wall, but for 4 meter panel we are considering. So whatever earth pressure and differential water pressure we are calculating, that should be multiplied by 4 meters. Next. So when the ship is tied here, there will be a mooring force. The mooring force is about 1500 kilonewton, the force will be 1500 kilonewton, but that 1500 kilonewton will be distributed for 3 panels. Each panel is 4 meter, so 3 panel is 12 meters. The bollard spacing is 20 meters. So suppose I am pulling from this center point of the table, it will not go only in the panel here, it will distribute to adjacent panels also. 3 panels we are taking, so 1500 kilonewton we are dividing it by 3, that is why we are getting 500 kilonewton. Is it clear to you? The bollard pull at a particular point is 1500 kilonewton, but that bollard will get distributed to 3 panels. So each panel we are doing a 500 kilonewton, but when you do a 3D analysis you will exactly get how much is going to each pile. Next. So this is the live load on this, which is about 50 kilonewton per meter square, but we are applying 200 kilonewton per meter. It is mainly because we are taking a 4 meter width. So whatever load coming on the slab, which is 4 meter this side, it will go into this. You have to see the axis here, x axis is along this line, y axis is vertical, and z axis is perpendicular to the plane of this paper or laptop. So it will be perpendicular to this. When you say minus sign, minus is opposite to the positive y direction, that is why we are giving a minus sign. The previous slide we have given bollard in this direction, that also we have put minus because positive x axis is like this. So this sign convention is very important, and the loading what you give also important. When you are giving the load as kilonewton and length as meter, you have to consistently follow for Young's modulus, for cross sectional area, everything meters and kilonewton. Next. So we have to do the analysis for different load combinations. So we will not some of them will act together. So this is one such combination. So we are combining dead load, live load, mooring force and earth pressure and differential water pressure. So this is the most the live load means stacking of some cargo and other things. This may come at some time, this may not come at some time, but permanently your soil will be here, your weight of the structure will be there. So we have to do this for dead load plus earth pressure, that is shown here. So here we have listed the various load combinations. The load factor is limit state load. So this is one such load combination. We have two methods of design, one is known as working stress design, another is known as limit state design. So when you do the combination, some of the loads, the first load is a dead load, we apply a factor of 1.5, the second load is the sixth load is live load, for which also we apply a load factor of 1.5, second load is the earth pressure, for which we apply a load of 1.0, third load is earth pressure on the retaining wall 1.0, and this is differential water pressure 1.0, this is a mooring force 1.5. There is a reason for applying different load factors. For differential water pressure we assume 1.0 because we are very sure that the water pressure load may not increase very much, whereas dead load, mooring force and live load, depending on the situation there will be some variation in the load, there can be an increase in load. Live load, when it is designed for 50 kilonewton per meter square, they may stack a cargo more than its capacity, that time it is likely to increase, for that only we give a factor. Active earth pressure also I will explain, when the deflection is increasing the active earth pressure will go to a limit. So this I will explain in the next class. Now he will show how to generate this discretization. We will start from the beginning and show how you can do this. No, create the model. We are starting a new problem. Go slow. So this is the screen which you will be getting initially. In this plane we will be putting the piles, diaphragm wall and vertical pile and raker pile beams.
Change the level to 3.85.
Whatever it is, we generate. Two meter you have to create, no? Where is it?
Just rougher than calculate.
Correct about 2.5 second one. So this is the top deck which is modeled. He has given some random number. Now we will put exactly how much we need. The distance between the C side to this first row pile is 2.5. So he is now made it 2.5. From the first pile to the diaphragm wall is 3 meters. Actually he is reducing it by 1 meter, so the 0.5 meters, so that it becomes exactly 3 meters, and the distance is 9 meters. So we will increase it by 3.5 meters. .75. One more 2 meter here. Right. Connected. So this is the way in which we have to give the graphical input. You can enter the coordinate also, but this will be much easier. So this is the C face of the beam, then we have the first row of pile, then diaphragm wall, then second row of pile, third row of pile and the raker pile. Or is missing, I think. This distance is more. Okay, we will correct the distance. So here we will be adding one pile, attaching a pile here, then diaphragm wall will be attached here, one more row of pile will be attached here, one more row of pile will be attached here. The distance between this first row of pile and the second row of pile after the diaphragm wall is 12 meter, so that we will have one crane here and another crane here. Now he will model the piles. It is a pile which is model, next it will be the diaphragm wall, this is another pile, this is the next row of pile, then there will be a raker pile. Raker pile means it is an inclined pile. The x coordinate will be depending on the raker, the x coordinate will be different. So he will be joining the top node to the bottom node. Now you will assign the diameter and the size of the members. So we are giving a rectangular beam 1 meter by 2 meter, 1 meter in the depth direction YD, ZD is perpendicular to the plane of this frame, 1 meter is the width of the beam. This is for the diaphragm wall. Thickness of the diaphragm wall is 1 meter, that is given as 1 meter. Perpendicular to the plane of the frame is 4 meter, that is what is given here. So we are assigning for the piles 1 meter in diameter. So we have to assign the properties for each member separately, what we have created. Show the rendering view. So now we rotate. Now this is the model what we have created. So there is a end beam we have to create, retaining beam we create. Shift it 2 meter away. അതിനെ പോട്ടെ. Three D view. Now we added one retaining beam. So that beam is shown at the end. Now you will assign the boundary conditions. We will assume the boundary condition as hinged at the bottom. Okay, tomorrow we will see the springs and the results also. Just go. So in finite element method I will write briefly what are the data that is required. Whatever he has done, we will give this following sections. One is called as the nodal coordinates, another is known as member connectivity data, geometric properties, material property, boundary conditions, loads, load combination. Then we will have analysis. Here we can have a static analysis or a dynamic analysis. Static we have a special analysis called as P delta, this also. These are the things which you have to learn, but it takes time to learn this. You should have a formal knowledge about finite element analysis. How many of you have taken a finite element course? How many are planning to take a course? No one wanted to study finite element. If you are in IIT you should take this course, finite element. All branch of engineering only, civil mechanical. Most of you are taking this course as free elective, but you better take finite element course also. You please read some textbooks, and Staad Pro manual you have to give this nodal coordinates, member connectivity, geometric properties, material property. Geometric property means moment of inertia, area of the section. Material property is Young's modulus, Poisson's ratio. Boundary condition means whether it is a hinged support, fixed support or spring support. Loads, various loads which we have discussed, then the combination of the loads. The analysis we can have a static analysis or a dynamic analysis. This is to calculate the natural period. Once you have the natural period only you will have the seismic force. We will see tomorrow.